transfer function in the way written as in Laplace can also be written by solving the solutions for the numerator and the numerator and the denominator. So the poles are the solutions of the denominator and the zeros are the solutions of the numerator. So the solutions of the denominator, look, they are just like this. We had this one, remember? This one 0, no excitation. Then we have this. This is called the homogeneous differential equation. And this is what we are solving when we say the homogeneous differential equation. And this is the particular solution. So the zeros. So I already told you that we have a non-zero output signal. We can have a non-zero output signal in the absence of excitation. That's what a dynamic system is, and that is the result of energy storage in the system. The zeros are the complex frequencies at which there is no signal transfer. So you see here, the zeros are the solution of the numerator equals 0, and poles and zeros must always be real or complex conjugate because they arise from real coefficients of your differential equations. So how do we characterize it? Well, a pole zero plot we usually do like this. We have the complex plane. A zero is just a circle and a cross is a pole. And this is how we say, well, this is like the Laplace plane and we have zeros and pole. How does this relate to what you probably know, like Bode plots? That's what I have in this picture and in this formula. So if you want to make to calculate the magnitude in the Fourier domain, not the Laplace, Fourier, which means frequency is along the vertical axis, that is the x-axis. The vertical axis in this Laplace plane is the x-axis in the Bode plot, the frequency axis. Then we are doing frequency here and we have to measure the length from this g omega to a 0 and from a g omega to a pole and divide it. That's exactly what we are doing. The length is the length of the vector from P1 to the point at which you want to know the magnitude of the transfer. And the phase of g omega is h g omega is the angle of the numerator minus the angle of the denominator. So it can be found from the angle phi 1 minus phi 2 minus phi 3 at this frequency. So moving along the vertical axis, viewing the angles and the distances to the poles and zeros makes it possible to get an impression of the Bode plot from the pole zero diagram.